Hi everyone, my name is Lucille Delisle, and I'm super happy to present you pyGenomeTracks. I don't know what is a fraction of people that already heard about pyGenomeTracks, probably a large portion, but there are still new people, so I'm always happy to present this tool. So first, what is pyGenomeTracks? pyGenomeTracks is a tool that is developed in Python, and it uses Matplotlib. So it enables reproducible and standardized generation of images at given loci of interest. So it's not a browser, you just need to decide which region you would like to plot, and then you have this type of plot that you can see on the bottom. It enables the right alignment of multiple annotations. For example, if you have genes or region of interest, and you can make all aligned. You don't need to go in Illustrator or Inkscape or any other vector software to make sure that everything is aligned. It gives you exactly the good image because it's highly customizable. So I would say that there are three main cases where you could use pyGenomeTracks. So the first one is when you're ready to publish, you know what you want, which abstract that you would like to show, and then you just use pyGenomeTracks to make it in your publication. So I show you here an example in Nature where they use pyGenomeTracks to show that there are some regions that were conserved within potatoes, but not with tomato. And they can highlight these regions in gray and show the different coverages. So this would be the first case, I would say, when you want to compare either different tracks for different epigenetic marks, for example, or if you want to compare two conditions. But I think it's still useful for other cases. For example, it can be useful if you want to visualize the coverage to do quality control. And I included one of these examples in the Galaxy Training Network for reference-based transcriptomics, because sometimes you have RNA-seq and you don't know what is the strandedness of your library. So a way to estimate if it's unstranded, stranded forward or reverse would be just to choose one gene, display the coverage of the forward or the reverse on this gene, and then just compare the two. So you can see here on the left, you have the coverage for two different samples. On blue, it's a forward strand. On red, it's a reverse strand, and you can see that they have the same level, so it's unstranded. On the contrary, on the right, if you look here, you have no coverage, and the corresponding reverse would be this one, where you have high coverage. So you can say this RNA-seq was done with a stranded library, so reverse. You can also use it to evaluate the signal-to-noise ratio. If you're doing ATAC-seq or ChIP-seq, whatever, you don't have a lot of peaks and you wonder, well, why don't I have so many peaks? And then you look at your coverage and you say, okay, this was not the best ChIP I ever did. And finally, I think it's very useful when you do genomoid analysis. For example, if you're analyzing splicing, it's very important to have a visual quality check. So your software gave you a list of hits, but I really like to go not one by one, but select the most promising targets and just check visually that you can confirm that you indeed see the differences at the coverage level. I give you here an example that I put also in the Galaxy Training Network, where you have this small exon that is used only in one transcript. And you can see that it's used in this condition, but it's not used in this condition. And so this way you can really confirm visually that indeed there is an alternative splicing happening between these two conditions. It can be also useful if you want to detect some mapping artifacts, or if you have some gene annotation issues, you can see the coverage goes beyond your annotation, or on the contrary, is very short compared to what has been annotated as your gene. The pyGenomeTracks is already quite popular. If you look at the GitHub repository, we already have 800 stars, only half of Galaxy. But I was surprised to see that there was only 1,800 for Galaxy. We published this work in Bioinformatics in 2020, and since then we have a high number of citations. So there are already a lot of labs that have adopted this tool. I can just show you one of the last published example. It was in Nature, and they used pyGenomeTracks to see different histone modifications on a given loci. So you can see that it's highly customizable. You can choose really the color you want to match the color code that you're using for your whole article. At the implementation level, pyGenomeTracks is highly modular. So that means that you have some modules. Each module would be a Python class. It would be a track type. And then you can add more modules if the one that you would like to plot is missing. So here is a global view of what is already implemented. So for example, what you can do is you can put an x-axis, very useful. You can put some scale bar. You can also have some high C display as triangles, but you can also display them as square if you prefer. You have the bedbrush matrix. You have different ways to plot annotations, genes, tags, whatever. The chromatin state. You can propose some coverages. You can add horizontal bars. You have the peaks. You have some links. And if you look on the right, you see the zoom of this. You also can plot math, which is a way to represent if the region is conserved through evolution into different species. And you can also do some vertical highlights if you're interested in some peaks or in some regions or whatever. And during last year, I got 2 pull requests, one for GWAS track and one for the sashimi track. Unfortunately, last year I didn't have time, but I promise I will take care of them, and there will be a new version soon. So how is it working for the user? You have 2 ways to use pyGenomeTracks. Either you use a command line. So for the command line, what you need to set up is a config file. So you need to write a configuration file that will be in the ini format that will describe from top to bottom what do you want to plot. And for each track, what is the customization you want. Then you just use the command line and you generate this type of plot. In Galaxy, magic, you have a tool wrapper. So then it's super easy. Your data sets are on the history and you just put them on the good track. So you choose which type of track you want, and then you just have the different options that are displayed to you. So for example, if you want to display an annotation, you have all this type of way to display your annotation. And depending on the choice you do, you will have very specific options that will be proposed to you. So if you choose to display it as inversion, so with 2 arrows, then the choice would be what is the size of the arrow, what is the width of the line, how would you like to plot the labels below. On the contrary, if you want to put everything on one line and with a collapse, then you have, what do you want to plot the labels? Do you want to plot all the labels inside the plotted regions, etc., etc.? So every parameter only appears if it's relevant to your choice. So in total, this input section is 1,000 lines of code. There is 22 conditionals, and this was done by hand. If you want to use the command line, you need to go to the read the doc documentation, and you need to read which are the different options. And this is, I would say, much for advanced users. So for me, pyGenomeTracks and Galaxy works very well together, because most of the users would start by using it in Galaxy, where they have different choices, and where they are at ease enough, they may switch or not to the command line. So for me, Galaxy allows non-command line users to access to this tool, which is pyGenomeTracks. It enables direct integration of the plots at the end of the workflows. So for example, in the IWC workflow of HiC, there is a pyGenomeTracks plot at the end, just to see the signal to noise. There is, if you use it in Galaxy, you don't need to download your input files because they are already on Galaxy. And it allows you to find the good parameters without looking for the options in the documentation. On the contrary, if you use command line, you can script, so generate your config file semi-automatically. You can also define the plotting region automatically, and you can generate frame for movies. So I just wanted to share with you what we've done with Osin Rekai from Denis Delisle. I don't know if it will work. No, because I need to switch. Yes. So he did some acetylation chip at different time points, and using pyGenomeTracks, we could plot exactly the same frame for the different chip. We also did a linear regression to be able to have the missing time point. And then you can really see how the acetylation invades from right to left on this OXD glossary. So pyGenomeTracks is on Toolchat. There is a new version that has been published yesterday on Toolchat. So it will be soon in newsgalaxy.eu next week. And we are developing it on GitHub. So this is the place where you can report bugs, if you are through reporting issues, but you can also contribute if you feel like you have an idea of which track would be good to be included into this project. You can make a pull request. And with this, I would like to thank all the founding that were included in this project since the beginning, because it started as a High-C Explorer module, and then it became independent to be pyGenomeTracks. And I would like really to thank the Galaxy community that always gave good inputs on this tool, that always go in both directions, both in the command line and in the Galaxy. And I would like to thank the University of Geneva, where I'm part of now. Thank you very much for your attention.
Hello, Lucille. Any questions?
Quick question, how many frames was needed for the video?
How many? So the question is, how many frames was it for the video? I can't remember by heart, but I think it was something like 30 or 40.
Okay.
Any other question? I'm sorry, I might have missed it, but is there an option in the Galaxy tool to generate as an additional output the config file so that you later can use that on the command line?
So, yeah, good question. So the standard output of the job is the config file. So you can indeed use this. You need to adjust the path, of course. But yeah, if you go to the Galaxy tool and you click on the info and you get the standard output, then you exactly have the config file that have been used to generate the plot. So usually that's true. The user that come from the Galaxy and switch to command line, they use this as a template.
Okay, then please let's thank again Lucille.